Okay, so now we will take a physical example to understand what this gradient represent in the physical world. Okay, so suppose we have let's say a 2D surface. It can be a metallic surface. Okay, so, and uh, due to some heat source, there are different temperature on this surface, right? So we have a temperature field x and x, which is a function of x and y. This is the x coordinate and this is the y coordinate. So for the different values of x and y, the different temperature will be can be calculated from this this equation, this T of x and y. Okay, now what we have to do is to calculate the change in temperature. Okay, so we know that this dt is the gradient of this temperature T times infinitesimal displacement vector. This is the dot product, not the times. So this gradient actually represent the increase in the temperature. I mean, this actually represent this is a vector quantity. Okay, so this represent a direction, let's say n cap. And what gradient actually does, it represent the direction n cap, and in this direction, if somebody moves, let's say this is the n cap direction at this point. Okay, but for different point, that n cap direction may be different. Okay, so n cap itself may be a function of x and y, right? So let's say this point x and y. At this point, the gradient will represent this n cap direction. So if we move from this point to this point in this direction, we will see we will face the change in temperature maximum. Okay, so this dt will give the maximum value if we are moving in the direction of the moving the direction represented by this gradient. Okay, so this is the physical the analysis of this gradient. Okay, it represent the change, it represent the direction in which the change in function is maximum. Okay, and one more thing that I can also mention over here, this T is the del of this T, not dl. Okay, so if you write it in the the magnitude form, so it will look like this. And cos theta, let's say cos theta is 1. Okay, so this is the our old familiar formula. The change in function is actually the rate at which the function change with respect to some variable times the change in that variable. Okay, so this represent the rate at which the function the field over here it is the temperature field changes when this L is changing. Okay, okay, so one more thing that I will tell you about this del operator. Okay, so we will take this this expression once again. Okay, so we will take this now we can also rewrite this expression like this. We can factor out this f Okay, okay, this f will not be over here. And this, and we know we have already write this as a del of f. Okay, so this f is factored out, that means this del operator is actually look like this. Yeah, remember one thing, this is only true for the, there will be z cap, this is only true for the Cartesian coordinate system. In the polar coordinate or the any other coordinate system, the gradient of the gradient expression will look like